again good morning to everyone. So, we were talking about Michelson interferometer, okay, and it is clear. Okay, there was one query after the class got over that when delta lambda, which is here, right, delta lambda, which is nothing but L1 minus L2. So, this L1 minus L2 as it has been represented in terms of here wavelength, right, which is input wavelength from the light, and this wavelength the difference sorry, this delta lambda when it changes to lambda by 4. So, actually it is to and fro, is not it? When I say L1 minus L2, but when light travels it will be travelling forward and return to and fro. So, total is 2 times, correct. So, basically it is lambda by 2, phase difference will be 180 degree out of phase with a wavelength difference means with a path length, total path length difference of lambda by 2. However, we are considering half the path length, right, because only one way to and fro is 2 L1 and to and fro is 2 L2. So, it will be lambda by 4. Okay. So, that is the answer. So, this interferometry approach is very useful for some of the biophotonics applications, and where is it useful? Basically to capture the phase difference, okay, between waves. But here you can see that our assumption is that the light source is having single monochromatic, right, wave frequency, single wavelength, okay, light source. It is very much theoretical, right. So, it generally any light source will have a certain spectral width, right. What is the meaning of spectral width? When we consider any light source, and if we see the intensity of the light with and its frequency component, we will see that it will have certain spectral width, okay, certain spectral width. Okay. So, this is in terms of frequency. Okay. Similarly, in terms of wavelength also similarly. So, that means the center wavelength, let us say we consider light emitting diode and red color diode, it may have a center wavelength around 630 nanometer, let us assume 635 nanometer. So, light emitting diode with a center wavelength 635 nanometer would be emitting a light, but it will have some bandwidth, okay, in terms of wavelength or right in terms of frequency, and that may be varying depending upon the configuration of this LED, the LED right material, its band gap characteristics, etc. There are various other parameters which will decide this spectral bandwidth, okay, in case of a light source. So, when the light source has such a spectral bandwidth and a frequency, right, bandwidth, do we observe this right as I keep moving? Let us say in Michelson interferometer, if I keep moving one of these mirrors continuously, do we observe continuously max minimum for right infinite distance? No. If it is monochromatic light source, we can observe, but if it has a bandwidth, then depending upon the bandwidth, this length up to which we can observe this change in the intensity as one of the mirror in the interferometer moves up to certain length, okay, and that has right a very important right application as well. Afterwards we will see at a later stage. However, so we are now very clear that if the light source has a certain spectral bandwidth, then the length of this intensity difference maximum to minimum right is limited. So, what will we observe? Let us say if this delta nu is very large, what we will observe in terms of the detector intensity, right. Where is the detector located? The detector is located here, right, over here, and it is observing the interference, right, pattern interference intensity over here, and that detector intensity with this path length. Okay, if we see when the path length is 0, we will observe maximum, of course, but what we will observe that as the path length changes, we will observe that if the light source has a bandwidth delta nu, the intensity variation will be very large when the path length is very path difference delta L is very small, almost 0 maximum intensity variation, but it slow it changes at this path length increases and it reduces to some average value. Thereafter, even if this mirror is shifting and delta L is increasing, the intensity will not, the difference in the phase difference, the intensity due to the interference, is not observed, change in intensity, because now the interference ceases to exist. Okay. So, this this path length where the intensity reduces to its half of its maximum, okay, half of its maximum, this average intensity, that is known as coherence length, okay, which is LC, okay, which is treated as LC. Okay. So, when we consider a monochromatic light source, coherence length is almost infinity, very long. Are you clear what it means? I keep changing this mirror position, correct, I keep changing, I will keep observing maxima minima continuously. Okay. But when I use a light source with a bandwidth delta nu, I will observe this intensity variation for a small length which is known as coherence length, and then it ceases. So, how do we estimate this coherence length? Now, the coherence length also depends upon, because this is intensity pattern, and intensity pattern also depends upon the spectral characteristics as well, correct, as well. So, of course, if the spectral characteristic is flat, that means if the intensity is constant for a certain wavelength range. Okay. So, for example, if we have a light source with a flat frequency range. Okay. So, this is intensity of the light source, this is the frequency, and this band is within which the intensity is almost constant. So, it is a flat spectral characteristics, and this is something different. Okay. It can be Gaussian, it can be Lorentzian, it can be void, this spectral characteristics, okay, they may be different. So, this characteristics can be Gaussian or Lorentzian depending upon the characteristics of the material, etc., etc., may be different. We are not considering these aspects for time being. Let us assume that we only consider some with some approximation right, and we will not include this, okay, for time being. Let us say this beam intensity profile with respect to frequency if we do not include, but we just try to derive what is this coherence length LC as far as, right, this spectral width of this any light source is concerned. So, approximately it can be derived by, we know frequency is nothing but C by lambda, right, frequency, right, frequency of any electromagnetic wave C by lambda. So, in terms of spectral width, in terms of width, right, frequency width, it can be given by C by lambda square delta lambda, correct, it can be given by this one. Is it that is okay? This is right, you take a differentiation, you will get. I am not considering minus sign over here, because anyway it has a bandwidth which is not negative, it is right, positive. You got this? Do you you can derive? Okay, very good. Now we also know that according to the Fourier analysis, okay, basically if you see here, right, the frequency information is converted into right, basically the frequency information is converted into temporal information over here, isn't it? Because length, difference, time, etc. is temporal. We know relationship between light waves traveling with a certain speed. What is the relationship between Z and T? We know, right? So basically this, if we see in terms of Fourier analysis, okay, then optical source with a frequency delta nu, okay, with optical source with a bandwidth, optical source with a frequency bandwidth delta nu delta nu can be given by 1 upon delta t, and this delta t, right, it represents what it represents, that the delta t is the time band, right, in terms of time bandwidth. The phase of this frequency is starts changing and it is different, okay, within this, okay. What it means, see, just physically what you mean by this, let us say there are two waves, lambda 1, lambda 2, okay, lambda 1 and lambda 2, two waves. If wavelengths are different, right, that means what, if I draw, of course I may not be able to draw perfectly, but I'll just, right, just, so let us say both these waves start with 0 as the reference, okay, see, okay, lambda 1 wavelength, okay, and lambda 2, it is slightly different from lambda 1. So, okay, like this. When they start traveling, they start with 0 as the reference position, they start, right, propagating electromagnetic waves. Initially they are in the same phase, correct, starting point, but depending upon the difference in wavelength, slowly the phase will change, right. That phase difference is indirectly related to the wavelength difference, frequency difference, etc., isn't it? If the wavelengths are very near, you will observe that both of them, although there is a phase difference, but it is so small that the significant phase difference will observe when they travel for little longer distance. Here both these waves are nearby wavelength, but still it is so significant you can easily observe the phase difference over here, right, the maximum over here, and now it is different, is not it. But if the wavelengths are too nearer, lambda 1 and lambda 2, what you will see, this phase difference will be so small when it travels. So, you will see this significant difference when it travels for a longer distance indirectly, right, and that phase difference when it comes in terms of complete phase change between two waves is known as approximately coherence length, and it can be given by this, right. So, delta t over here indirectly indicates the coherence, indirectly indicates coherence length. Okay. So, right, what is delta t? Delta t is equal to C delta L by C, isn't it, small distance change, and this delta L is nothing but coherence length, okay, approximately, are you clear, approximately coherence length. Now, this is all approximation, I am not at all knowing what is the real intensity distribution, etc. In fact, it is little bit complex in terms of we will have to do Fourier transform and try to find out for each of this frequency what is the intensity component and how it reflects in terms of coherence length, but for time being delta t is this. So, indirectly, so this is nothing but I can represent this delta nu 1 upon delta nu as lambda square C delta lambda, correct. 1 upon delta nu is this. So, 1 upon delta nu is this, which corresponds to delta t, right, which corresponds to delta t, which is nothing but delta L C by C, is not it, correct, this form, is it okay. So, so basically delta nu is C by coherence length, right, this length LC, delta LC, or using this to combine, you simplify, what you will get, delta L coherence length is nothing but lambda square by delta lambda, correct. C will get cancelled out, is it okay, C will get cancelled out, delta L is coherence lambda square by delta lambda. So, approximately if delta lambda, which represents the spectral width, if it broadens, then the coherence length decreases, okay. So, if this delta lambda is very small, coherence length is very long, okay. So, that is what you could observe. So, this basically interferometry approach helps us to determine phase difference between two waves, and only thing is that if the wave is a laser or a spectrally narrowed wave, we will be able to observe for a longer distance, longer coherence length, this phase, okay, change, okay, etc. So, in case of Mach-Geander interferometer also, you will be able to observe the similar thing. Only difference between Michelson and Mach-Geander interferometer is, so if I quickly draw the configuration, I will, so if there is a light source comes, and then I use a beam splitter over here, a beam splitter which allows transmission of light and reflection, and then I use 45-degree mirror M1, and over here it travels and again 45-degree M2. So, this light will get reflected over here, it will and if here again I use a beam splitter. So, this light go here, part of this, the part of this light, okay, will also get transmitted and get reflected, and this also will get transmitted, correct. And so, this is nothing but a beam splitter, okay, beam splitter. So, here also beam splitter, here also it is beam splitter, okay. And so, here in case of Mach gender, as compared to the if you compare Michelson interferometer, the one advantage is in case of Michelson interferometer, the reflected light travels back over here towards the light source, okay, towards the light source. While of course, part of it will go to the this right 90 degree, but part of that will get transmitted through the beam splitter and come back. So, that can be avoided over here, because here the reflected light will not right, it is going outside, right, it is not coming back over here. So, generally when we are considering Michelson interferometry approach and you do not want this noise to interfere with the light source, we use optical isolator in between, okay, optical isolator. So, what optical isolator does is it is acting as an optical diode, it allows transmission of light only in one direction and not the other direction, okay. The configuration is we can see it afterwards when we come across, but for time being it is an optical isolator which is used, while here we do not require such optical isolator. However, there is another, there is limitation. If I want to move this mirrors or change this configuration, it is bit right cumbersome, little difficult, which is not the case with the Michelson interferometer. And there is so that this is Mach gender interferometer, okay. And what will we capture? See, all these interferometers, they depend upon basically the phase change measurement, basically phase change measurement which can be captured. So, let us say we consider either Michelson interferometer or so this is Michelson interferometer or Mach gender interferometer. What we will observe that how can we make use of it in biophotonics or various applications in different ways, but one very easy simple way. Basically, interferometry approach is used to capture the change in coherence, change in not coherence, but the phase, I am sorry, change in the phase between the two light optical electromagnetic waves travelling in these two arms L1 and L2. Here the arm L1 is this much, right, length, and arm L2 is this length, okay. Both of them are equal in case of Mach gender interferometer. So, you will always see constructive interference. However, if let us say in this arm, when light is travelling through this arm through a particular medium, let us say there is a medium here whose refractive index is different, okay. So, there is a change in refractive index as compared to N0 all around, okay, all around. So, this in this arm, the light which is travelling in arm L1 is experiencing refractive index N0, while the light travelling in arm L2 is experiencing N0 and in some part of this, right, this arm, part of that is experiencing N1 as the refractive index electromagnetic wave. That means when it travels through the same this distance in L1 and L2, but due to the refractive index change, right, 2 pi, so path length phase change is 2 pi basically, right, by lambda into n1. Okay, let us say what will I do, simplify, for simplifying, otherwise of course we can write in complex way, but let us assume this whole path as refractive index n1, and let us assume that the whole this path has refractive index n2 n1, and this is let us say n2. So, what will happen, delta phi phase difference between both this waves is 2 pi by lambda n1 L1 minus n2 L2, correct, L2, okay. So, L1 and L2 may be equal, okay, they are equal, however n1 and n2 are different, and the phase difference is captured in terms of intensity difference, isn't it, we have no. So, these aspects are basically you can make use of this type of interferometry approaches to determine the phase change via the measurement of via the detector intensity change, and then compare it in terms of phase change with respect to the some change in the along this arm, maybe a temperature change which changes the refractive index, maybe a pressure change along this arm which changes the refractive index, maybe some other material properties are different which captures this refractive index change. Okay. You can also introduce similar thing over here, L1 with refractive index N1 and L2 with refractive index N2. So, the phase change over here will also be similar to this N1 L2, okay. Depending upon the difference in N1 L1 N2 L2, all this, right, parameters, we will be able to capture the information related to right, interferometry. Now, this is what I explained to you is in the free space, right, aspects. However, if we try to see in optical fiber, the configurations are quite similar. So, in case of optical fiber, the light is coupled to the optical fiber by right, light source with the lens or some coupling optics with the fiber, okay, it is coupled. Now, that light when it passes through a coupler, now optical coupler has 4 let us say right, sections. One, it can couple, it can allow input here, and then that input, right, is will go into this arms, okay. And when the reflected light comes, it will get coupled to this arm, okay, this arm. So, input is from here, and the coupler allows 2 by 2 coupler allows light input to get divided into 2 arms, and so L1 arm and L2 arm, they travel light electromagnetic wave travel depending upon the waveguide or optical fiber, right, length, etc. Then when it reflects back, it will travel, come to this coupler, and the output is from this, in this, okay, from this fiber it is captured. Now, as I told you, if there is any change in one of this arm, let us say this is a sensing arm, something changes over here, then the phase change resulted phase change in the phase due to this some physical right parameter change is reflected in terms of the phase change between the two reflected waves, right, from arm L1 and L2, and they are being captured using this analyzer, okay, detector, okay, output. So, this configuration is what I have explained to you over here is very similar to the Michelson, right, configuration. Only thing is that the light travels only in one direction, okay, with this coupler, right, one direction in the input in this way, output through this fiber, okay, through this fiber. Now, the same this configuration can be converted into, right, Mach gender, right, configuration. So, there is a coupler which divides the input light into two arms, then it travels, and the coupler over here will combine this light. So, this is, right, demultiplexer, this is multiplexer, very similar to that, okay. So, light is getting coupled over here to this fiber, and then detector is placed over here, and which detects basically the phase difference between the light traveling along light path 1 and the light traveling along light path 2. The phase difference will result depending upon length of this light paths, okay, L1 and L2, or physical characteristics of this, right, when it changes due to some other parameter change, okay. So, that can be captured, okay, over here. So, this interferometry approaches are used for various biophotonics, right, applications. So, now we know right, one more aspects, not only polarization, need not be only amplitude or intensity change, it can be phase change which can also be captured using this approach. There is one more, of course, if you right now, so if you see, we talked about electromagnetic wave traveling in the free space or through waveguide mode coupling, then we talked about some evanescent, right, intense, some law of output input in the waveguide may get coupled with the clade region also, that can also be used to detect something, it can also be used to capture the phase change parameters, etc. There is one more approach which is based on fiber brick grating approach, okay. So, let us try to see, time is, yeah, there. So, I will quickly get into optical fiber based, but using a fiber brick grating as the, right, approach. So, see, so this optical fiber brick grating basically works on the principle of distributed feedback, okay, distributed feedback. So, what it means in a, right, let us say this is the fiber, this is the core, okay, core, sorry. So, light is there, couple the fiber, and let us say this is sorry, 1 minute, it's you need not change anything, I'll draw it with which has a core and a clade. Okay. So, there is a core, this is the clade, optical fiber through which light is transmitted. So, now this light which is getting transmitted, and if I induce a grating structure over here. So, what it means grating structure is I induce by some means a refractive index change in this core region, okay, periodical refractive index change. That means the refractive index is periodically changing over here, right. So, there is a small refractive index change, and that refractive index change, let us say in terms of let us say core refractive index over here in the y axis, let us assume, and this is the fiber axis, okay, through which the light is transmitted. So, in this region refractive index change is not there, okay, no change. However, in this region there is a small refractive index, and again there is no refractive index change, okay. I introduced like this. Now, what happens whenever there is a refractive index change, and if the light is travelling like this, and if there is a refractive index change between n0 and this is medium n1, what do you expect? You expect some part of the light to get reflected back because of the Fresnel reflection, right, impedance matching, very similar to the approach impedance matching. Now, if there are multiple such, right, changes occurring, what do you expect? Some part of the light will get transmitted, some will get reflected, some part will again transmitted, some will get reflected again, it will get transmitted, it will get reflected, it is very complex, right, phenomena. Lots of reflections are occurring between these various such steps, each one changing n0 becoming n1 over here, then again becoming n0 in the intermediate stage, again right, it becomes n0 here, then again n1, n0, n1, it's right, it is right, it is changing, refractive index is changing, as you can see. So, this is very similar to, you can derive that the reflection will be maximum over here, it will be maximum when you achieve a Bragg condition. That means of course, Bragg condition with 90 degree is the wavelength. That means we know what is the Bragg's equation in case of any material, if the light is getting, right, transmitted and get reflected, light reflection over here, right reflection from the bottom with the d, this is theta. If you can recall Bragg's equation for X-rays, etc., you would have derived for the crystalline characteristics, you try to derive this. So, which is m lambda is equal to 2 n d sin theta, okay, m lambda is equal to 2 n d sin theta, okay, sin theta. So, what it means, m is the order, 0th order, first order, second order, this, okay. So, this may be, let us say 0th, second order means further it can go to next, right, multiple. Lambda is nothing but the input electromagnetic wavelength. N is right over here in case of grating structure, etc. N into d represents optical path length, n is the refractive index, d is the distance it travels, and theta is this. So, if you consider this with a grating period of lambda like this, and you consider right, you consider the first order m equal to 1, first order length. So, let us say if I put it like this, m is 1, d is nothing but the lambda, okay, theta is 90 degree, right, theta is 90 degree, then lambda is equal to 2 n into this lambda, correct, from this Bragg's equation, from the Bragg equation. Lambda is the optical electromagnetic wavelength, right, it is wavelength. What is n? N is the refractive index of that, right. It is in our case it is an average refractive index n1 plus n0 by 2 approximately, okay, little. And what is lambda? Lambda is the period, grating period, okay, grating period, okay, so which is shown over here. This is the lambda, grating period, okay. And this equation is the one where the reflection will be maximum over here, reflection will be maximum. What it means? Let us say I am sending wavelength lambda, and if it satisfies the equation, this equation, if the fiber grating period is lambda and refractive index of this material is such that, fiber is such that lambda equal to 2n into lambda, then this wavelength lambda will get reflected back, will not get transmitted, but it will get reflected. That means if I am sending different, let us say this is grating period, okay, with lambda as this and lambda 1, lambda 2, or with different color. Here, one more minute, I'll lambda 2, then, and if lambda 1 is satisfying the condition, this the optical fiber, while lambda 2 is not satisfying this condition, same period and refractive index observed is, right, approximately same, then in that case what we will see that lambda 1 will reflect back through this medium, okay, will reflect back, while lambda 2 will get transmitted through this fiber, will get transmitted with slightly, right, this way. Let us say my input spectrum is very broad, it is a broad band, okay, and this fiber grating is such that it satisfies this condition is satisfied, this Bragg condition satisfied for the yellow part of this spectrum, okay. Then the reflected light will see the yellow, right, light spectrum, while the transmitted one will see this broadband spectrum with a deep over here, which corresponds to the reflection from this, right, spectrum. And now if by chance if the characteristic of this medium changes, okay, either the material gets strained, so this lambda changes to lambda dash, then accordingly the transmitted wavelength will also change, or the reflected wavelength will also change. If the medium surrounded by this refractive index changes over here, then correspondingly the reflection etc. can change, okay. So these are the various ways which can be used along with the optical fiber waveguide structures etc. to get some information about change in the length, change in the refractive index, change due to some strain, change due to pressure, change due to temperature, because if the temperature changes, this length is going to change, right. Refractive index will also change, length will also change, optical fiber length etc. Then automatically the wavelength will, the one which is getting reflected back will change, because the Bragg's condition will alter the wavelength which is to be reflected, okay. So we can capture various such physical, right, measurements, parameters using this indirectly a phase change, but reflected in terms of intensity change of a particular wavelength. Is it, am I clear? So in the next class I will just explain about one more type of fiber, which is recently it has come out, it's being used for various applications. We will try to see that fiber some simple right configuration, then we will proceed towards various light sources, which I intend to cover in this week before we go to the real right understanding of biophotonics applications. Okay. So, with this thank you very much.